everyone. In this class, let me compare the magnetic fields produced by solenoid and bar magnet. One is, if we compare the magnetic field lines, I am showing you the magnetic field lines, just see how similar they are. Another way, we have done it in some other class, that if we have to find out the magnetic field produced by a bar magnet on the axial point, if I take some point here at distance r from the center, then the expression is this: along the axis and on perpendicular bisector, it is mu naught by 4 pi p upon r cube, magnitude wise, otherwise we know here this. On perpendicular bisector, the magnetic field direction is opposite to the field of the dipole moment. Okay. So, and what is the dipole moment? It is defined again exactly the way it has been done for electric dipole. Q into L is taken as electric dipole moment. Same way, magnetic dipole for it has been taken ML. L is the distance between the two poles, and M we call it pole strength. And then whenever, how to find out the direction of the field, we assume that there is a very small magnet at that point and then see in which direction it aligns itself. Or another approach that has been used in many textbooks, though it is not accepted in modern science, but even then, what they have done, north has been taken just like the positive charge here, and south just like negative charge, and then all the expressions, they are similar. So for the purpose of comparison, it will serve the purpose, but actually magnetic monopoles don't exist. So that's not the right way to derive the expression. But for comparison, eventually we get this expression even from the experiments. So how do we get this expression? We will drop that, whether we get it experimentally or by using the approach which is not accepted to. But even then, the final result is this. This is the magnetic field on the axis of a dipole moment. And I am telling you basically that is because very simple. When it comes to the purpose of solving your numericals, then that is okay. So QL, here it is ML. In electric dipole case, we know that positive charge experience force in the direction of the electric field, and negative charge, this experiences force opposite to the electric field. And how much is the torque onto it? P is sine theta. For a magnetic dipole, it has been defined as PB sine theta. Energy is minus PE cos theta. For magnetic, let me use these words, ME. It is minus PB cos theta. The magnetic field produced by a bar magnet or by a magnetic dipole is this: magnetic field produced by one pole. It is M by R cube. So just like 1 upon 4 pi epsilon naught Q upon R square, M by R square. So M by R square, here Q by square. So similar, charge has been replaced by the pole strength. So for the purpose of comparison, for the purpose of solving numericals, that's okay. But we don't accept this approach. The reason being that magnetic monopoles don't exist. So whatever way we do, This is the magnetic field on the axis of a bar magnet. Now let us see what is the magnetic field produced on the axis of a very long solenoid. We will take a very long solenoid and the diameter will take very small. Okay, we know the magnetic field produced by 2 pi I a square upon a square plus x square 3 by 2. This is the magnetic field produced by a current carrying loop at a point on its axis. Now here also, solenoid makes, it's a insulating material, it's an insulating material, maybe a cardboard, and then enamel copper wire that has been wrapped onto it. So it is a collection of a very large number of circular coils placed very close to each other. So let's take, we'll have to use the integration approach actually. At distance x from here, let us take width dx at distance x. Why will I have to use the integration approach? Because we have to find out the field due to a large number of coils, and the field is a function of x. So that's why we have to find out the magnetic field produced by few turns in some given length, let us say dx, and then integrate it for the limits of x, permissible limits of x, whatever they are. In this case, it will be minus L to plus L. Okay, so this is the field produced by one loop. I have taken at distance x or width x. So if n is the number of turns per unit length, so how many turns will be there in this? N dx. So the magnetic field produced by all turns in this section of thickness dx, it will be 2 pi I a square n dx. Mu naught by 4 pi, 2 pi I a square upon a square plus x square 3 by 2. This is the field produced by one turn. So produced by n dx turns. These are the number of turns in this length. N is the number of turns in unit length. So in dx length, it will be, so it is n by L dx. The total number of turns n, so this is n, so n dx. Number of turns in this thickness. Okay, now what is the distance of this part from this P? It is, A is the radius, let me take radius here also A, and now I want this distance A square plus, this is R minus x square 3 by 2. Okay, I need actually this distance. So it becomes A square plus R minus x. This is R, this is x. So this distance is R minus x. Observe carefully, this is the field produced by this section of the solenoid. I want now the total field. Total field will be the integration, and we know the magnetic field produced by a circular coil is along the axis. So this field will be along the axis, either this or this, that depends how the current is flowing. If the current is flowing like this, the field is like this. If the current is like this, the field will be this. Okay, so total magnetic field B will be the integration of mu naught by 4 pi 2 pi Ia square dx upon a square plus r minus x square raised to the power 3 by 2. Seems complicated, but we have to use the approximation. We have to consider that r is much larger than x A. Apply those things and then see what do we get. Limits for dx, from here to here. Where can we have first loop? Here at minus L, and last loop at plus L. So minus L to plus L. X may vary from this to this. Okay. Now see how many constants can be taken out. 2 pi I a square, and here if I am saying R is much larger than A and X, so the point where we are calculating magnetic field is away from this point. So it means here we will have, here I can drop X. So once I have A square plus R square, then I can drop A also. So it will become only R square raised to the power 3 by 2. This term will be R square raised to the power 3 by 2. So it will be R cube, and R is fixed. So even R cube is here. Now I am left with just integration dl minus L to plus L. So we are not integrating it for finite length, finite distance and all that. We have taken that the solenoid is very long and this P is far away from the solenoid. So it is simple now. It is X from minus L to L. So it will be I can do like this, so it becomes 2L. Okay, so this part will be 2L. So I am using here only into 2L. Okay, now what is the magnetic dipole moment for this solenoid? Let us come to that. Magnetic dipole moment for solenoid, NIA. N is the number of turns per unit length, and total length is 2L. So this is the total number of turns. I and A is pi a square. Just see this expression very carefully. Number of turns total, N is the number of turns per unit length. So total number of turns, how many? N into 2L, I a square. This is A. Actually it is NIA. We have already discussed all these things as the magnetic dipole moment for a loop is NIA. So for a solenoid it will be like this. Okay. Now let me apply here. So 2L N, where is N? N was here, oh sorry, it was dropped. N was here, okay, 2 pi I N A square dx is. So N 2L I pi a square. This is magnetic dipole moment. So it is actually mu naught by 4 pi 2 Pm upon R cube. So this is the magnetic field produced by a solenoid at distance R. And what is the magnetic field produced by a bar magnet? It is again same. So it means a solenoid and bar magnet fields are comparable. Solenoid can be considered as a bar magnet, or the other way, bar magnet can be considered just like a solenoid.